But of course, one could do that experiment. So you condense it and then have a C60 in your old finger and then record maybe the infrared spectrum of C60. But then we did record the infrared spectrum of C60 at that time, but not with this method. We just took the C60 and applied the film on a little KBR substrate. The C60 peaks are so sharp in any case, we didn't think there was much need to do all this fancy low temperature experiments. Okay. So I have these species produced, and these species now will travel. This is in vacuum. So in vacuum, the mean free path is quite large. The mean free path will be about many meters, depending on what the pressure inside was. So which means that these, once produced, they might collide right away when they come off, because the density soon after ablation is quite large. But when they're all expanding, and as they expand, then they get away from each other. And after a certain point, there is really no more collision, and therefore you will find C2 and the C3 once produced will essentially travel all the way down to as long as you want them to, and get deposited whenever they meet a surface. So what we do is we put a little KBR window, kept at 10 Kelvin. So these species would essentially come here and deposit here. But what we're not going to do is something little fun. While this ablation is going on, we have a steady stream of argon that is being directed onto this cold finger. So while these species are depositing, I'm also depositing argon at the same time. And I keep the argon flow rate sufficiently large so that when this freezes out over here, the argon is always going to be in excess compared with the carbon clusters that are being produced. So what I essentially have is these species being trapped in argon, just like acetylene was trapped in argon. I had this cartoon for you, policemen and little boys running around. The same thing happens over here. You have argon everywhere, and these C2, C3, C5. And mind you, all of these are extremely reactive species. If only a C2 got hold of another C3, it would react. If C2 got hold of oxygen, it would react. But why are they not reacting here? They're not reacting here because I'm not letting them react. I'm not giving them a partner to react, essentially. Because by keeping the system in a vacuum, they just don't have a reaction partner. So they continue to carry on and eventually will deposit here. And once they deposit here, they could react with each other. Oh, but then what I have done is brought an argon in between and simply isolated it from each other. So I now have a situation in which here is a C2, maybe a C3 here, and a C5 here, and a C7 here, and so on. And I have argon everywhere. So the C2, C3, C5, C7, all of them absolutely itching to react. There's nobody to react with. And that's the whole idea. And this is what I meant by saying this is the high temperature chemistry being studied in a low temperature technique. So I basically sort of got these two pretty much wedded up. Because all these species here are high temperature species. And where have they been collected? They have been collected onto a low temperature cold finger. But they have been insulated from reacting with each other by essentially having argon on. And of course, now if you go and take this sample and record an infrared spectrum, what's the infrared spectrum you're going to get? You're going to get the infrared spectrum of all these species, very reactive, and which have all been produced at 4,000, 5,000 Kelvin and so on. So you basically have angle, you basically have information on high temperature species, but you're basically using a low temperature technique to do that. And that's the whole idea of the title, low hot, low cold. Having hot species trapped in a low temperature sampler that we basically have produced in this experiment.
Excuse me, sir. Can you repeat again why the C2, C3 do not react with each other from the graphite rod to the cold finger?
They will probably react somewhere at this point, because at the time you're hitting them with the laser, the evaporation takes place. There are a lot of species right there at that point. So their density is reasonably large. So they will collide there. But as they get out, this beam actually expands. And beyond a certain point, the average distance between these molecules is quite small. And they're not going to encounter any species after that. So beyond here, all the way here, they're just flying from one end to the other with hardly a chance to interact with each other. If the vacuum over here is like 10 power minus 6 torr, then you're basically looking at a mean free path of 5 meters. The mean free path, the way to remember that is that 10 power minus 3 torr, the mean free path is 5 centimeters. These are good numbers to remember. So at minus 3, 10 power minus 3 torr is 5 centimeters. At 10 power minus 6 torr, it will be 5,000 centimeters, 5 meters. So on an average, a molecule is going to meet somebody else after traveling about 5 meters. My experimental setup is about half a meter. So they're not going to meet anybody till they hit the wall. So essentially, the only place they're going to collide with is the wall. They are not going to collide with any other species in the environment. And And that's the reason why a species once produced here and it has made it through the initial part, it is not going to be able to react with any other species. It will actually travel from here to here unimpeded. And the only place where it will deposit is on my cold field. Of course, some of them could travel in this direction, then you will see that they can travel, they can deposit here and here. And that's the reason why once in a while we'll have to take out your system and clean it, because you'll have these species all lined up. So they don't look dark, they don't actually have a nice color. Because it's all extremely thin films. You have these colors of thin films actually produced. But after a while you have to clean them up, because some of these species will actually travel off in very different directions. Because they're not collimated beings, they're just sort of expanding and going off in different directions, and therefore they will sit there. Because R1 doesn't sit anywhere, it will get pumped off. But some of these target species might line up here, might line up here, but a good number of them will actually come and sit here along with R1, which if you now record the infrared spectrum, you will actually get the infrared spectrum of these various high temperature species that are now being trapped and caged in a low temperature sample. The trapped reactor species actually live forever. If you didn't have this technique, the moment you produced it, you would have to study them because they are flying away. So before they flew away, you have to react, you have to study them. Or if you waited too long, they would react with somebody else. So essentially what you have to do is to have a technique that is going to be far faster in the lifetime of these species. But here the lifetime of the species is infinite. In fact, if you deposit it now and you feel like having lunch and coming back, you can. Or it is still waiting for you when you get back to do the experiments. These species don't die out simply because in this cage, the lifetime of these reactive species is actually infinite. Hence you can easily study. It's similar to laser ablation, thin film deposition. You see many people doing that, even I think in physics, so we have to go to sheet like that. What do? Is thin film deposition. They do the same thing. They hit the laser beam onto a sapler, onto a substance. It could be graphite, it could be gold, it could be any metal whose thin film you want to produce. You produce all these gas phase species, and these gas phase species will, let us say, the reds are the C2s, the greens are the C3s, and the C5s, and they will all get here and form, let's sit here. In this experiment, they are not sending argon there, so there is nothing to insulate them. So when these species actually go and deposit onto this thin, onto your substrate, they are actually sitting right next to each other. They are all reactive, so they will all react with each other. And what will you get as a result? You will get a thin film of graphite once again. So this is how thin films are produced by a laser ablation process. So what we are doing is almost very similar to a thin film deposition, except that we prevent the formation of the thin film by supplying a sufficient amount of argon, so that you don't have these reactive species. The precursors to these thin films are actually trapped in these argon beams, so that you can study what is being produced as a result of the laser ablation. So there is something very common, but the presence of argon is what sets it to apart.
Once these species deposit on the 10 Kelvin cold finger, they can't react with one another, but can't they dissociate? Each C5 cluster dissociate?
Okay, if they dissociate, they have to dissociate unimolecularly in the sense that they have to dissociate. So let's say if I have a C3 cluster, and if it's in a ground state, and let's say the ground state is bound, then of course they're not going to dissociate, because if I have to dissociate them, I have to take them up to a barrier which will then dissociate them. At 10 Kelvin, I don't have the temperature to be able to do that. So all these are stable species in their ground states, and once they are there, they will be trapped in the structure that they have produced. If they were so unstable that they would have to dissociate, they would probably dissociate right here, because there's a certain time that it takes to go from here to here, which could be on the order of a few microseconds. So if they had lifetimes less than microseconds, then of course they would dissociate right here. But if they survive that, then they're... Now if they want to dissociate, sometimes, I think I've mentioned this in a different talk, sometimes they can't dissociate because the cage will actually prevent them from getting away. So the cage will actually preserve the molecules very often from dissociating and keeping them.
So what is the thickness of such films?
The ones that we deposit, they are generally of the order of about 5 to 10 microns.
At least around 8 to 10 atoms.
Oh, many atoms. We're talking about micron things. So we are assuming that they are talking about it's quite thick. Now, it's rather easy to figure out what the question we ask. What's the thickness of the film I have deposited? It's not too difficult to figure it out. All you have to do is, at the initial phase of the deposition, if you shine light at a certain angle, you keep watching it, you will see the colors being formed as it deposits. So you'll see a red, then it becomes green, then it becomes blue. Again it becomes red, green, blue, because there's various orders of the interference change. So all you have to do is to see when you hit a red and when is the next red coming. And that is one link. And then see how much time it takes. And you get a rough estimate of what the thickness is. Can't afford to be colorblind to do that.
So the other experiment to study is about like constitution here. It's C2, C3, C5. Here it's all mixed.
Yeah, here they all get mixed up.
So what information can we get?
Oh, these people produce basically thin films, extremely thin films of the. But these films have, when you have thin films, you have a lot of surface as opposed to the bulk. When you have a lot of surface, intensive chemistry can happen. They can act as sensors for various materials and so on. So it's basically the production of thin films for various technological applications and various sensor applications that people basically do this. And the chemistry of thin film also is quite interesting in its own way. So that's basically what it is. So the thin film people don't put the R on, we put the R. And we essentially prevent thin film formation of the graphite itself. We basically have all these reactive species that are trapped and kept safe in the argon cage, the argon wall, you may call it. So we can go back and do these experiments on these species. In matrix isolation, this is what we get. In thin film, this is what we get. The white species here are the argon atoms. The same setup that I showed you earlier, you can see a little green out here. And that green is essentially because we were shining a second harmonic of a gas laser, 532 nanometers, which is green. And that is basically we focused inside to do the laser ablation. This is the cryostat. The material is inside here. The substance that we want to ablate is kept inside. The laser hits it, produces the vapors, and of course through this line we send argon, and the two mix and form your thin film. And once it is done, it is pushed into the spectrometer for recording your data. The laser that we use is one at least that we use is a neodymium gag laser with a wavelength of 532 nanometers. It basically lasers at the fundamental, which is 1064, which is infrared. But you can take the second harmonic, which is 532 nanometers. The intensity per pulse is roughly around 50 millijoules per pulse. The pulse was about 10 nanoseconds, and it hit the laser at 10 hertz, so it sort of hits you at 10 times a second. And the peak power, which is the power within the laser pulse itself, is about 5 megawatts, which is enormous. And the spot size is roughly around 100 microns. And how do you get up spot size? You just take a glass paper, you hit the laser beam onto it, it will form a burn spot. And you put it on a traveling microscope or something, or some microscope, and just measure what the burn spot size is. It will give you a rough idea of what the laser beam spot size is. So we estimated that to be roughly around 100 microns. We could make it down to 50 microns and so on by using appropriate optics. What's the advantage in laser ablation? Well, it's an easy method to get 4000 Kelvin, which is what I mentioned. It's containerless. The sample itself is its own container. So we don't have to have another container. And therefore there is no container contamination, there is no container loss. Container contamination is also a problem because while your material is evaporating, the container also is evaporating. And you have everything sitting on your matrix and you have no idea whether you are looking at the chemistry of your sample or you are looking at the chemistry of your container. Just imagine if the vessel in which you are boiling milk also dissolves the milk as the experiment goes on. Of course, the coffee is going to taste very different. You need a very small sample here. So all that you need is whatever the laser actually ablates and sends out, that's all. So after doing the laser ablation experiment, you remove it, you only see some burnt spots here and there. And you can return the sample to whoever gave it to you saying, no, look, I have used to take it. Basically, you have done the experiment. So there's very little sample that's required. So if you have extremely small amounts of sample, you can actually get away with doing this experiment. It's basically 4000 Kelvin. Just see this is an experimental model rate. You have 4000 Kelvin on one end, and about 6 inches away, you have a 10K substrate. Now, if I had a furnace of 4000 Kelvin and 10K, this 10K would never get to 10K because the heat load of this would keep heating this up, and this would probably be about 100K or something. Mind the specific heat is quite low and near 0 Kelvin, it just will shoot up in temperature. So it's actually a very difficult experiment if you had a furnace at 4000 Kelvin sitting right next to a 10K system. But in the laser, the spot size is 4000 Kelvin for a very small region. So there's really no heat load on my cryostat, and I don't have to worry about the cryostat heating up while the experiment is being done. So that's another very important advantage. So this is the spectrum that we got. Of course, this is nothing new. The whole world recorded by then. But the moment you set up a new facility, this is what we did, we like to know whether it works. So you take graphite and you record the spectrum and make sure that you get the same spectrum which the entire world is covered by then. You do it, and here you see a C3, you see a C5, you see a C7, all of these structures, the spectra were known, and we were getting them. They sort of told us that we were doing things right. And of course, we also have carbon monoxide, so we have very active carbon, very reactive carbon that's updated out, and any vacuum system, even if it's 10⁻⁶, there is some amount of moisture present in there. So at the time of ablation, it could react with some of the water molecules around, and you might get carbon monoxide being produced. And that's a nice peak of carbon monoxide. And not only that, you also have a C3 cluster interacting with the water to give you a C3 water cluster. If anybody told you, can you please study for me C3H2O and tell me what it looks like, it's very hard. How do you produce C3 and then look at water bounded to that? But here is an experiment where we didn't even want to do it. When the C3 was produced, the water was there, and we got the cluster, and we got the C3H2O complex. So you can study all these exotic complexes of very exotic species by this technique. But of course, having worked in a nuclear industry, we had to justify our existence over there, and therefore we said, let's study uranium oxide and see what we can get out of it. So we took uranium oxide material and we kept that as a substrate. We hit the laser onto the uranium oxide, and whatever came off, we trapped it in argon. And we said, let's see what we get. This is an important experiment really, because we got all the spectrum. We won't worry about the assignments of this, because that's not what I'm trying to do over here. But to tell you short, when you ablate uranium oxide, UO2 solid, what do you get in the gas phase? You get UO, which is uranium monoxide, you get UO2, and you get UO3, you get U3O8, and all these species. It's very important because this tells us that if the uranium oxide were ever to be taken to about 4,000, these are the vapor phase species you will get. So if there was a nuclear meltdown, if the material just got heated up to 4,000, you know a